All right, cool. So, Naveed, what is it again we were doing today?
Yeah, so we are today looking at a task which is called anomaly detection. Um, so the problem is presented um, in a way that we have, like, let's say, if we talk about the thing that we are looking at, if you have, let's say, a machine working in a factory or somewhere, um, it would be better if you monitor this machine before something catastrophic happens to it. So what would happen previously was like you would do the preventive maintenance. When something catastrophic happens, then only then you find out that it is something really bad is happening, has happened already, and now let's fix it. But with the rise of deep learning and machine learning, people are now shifting towards what is called predictive maintenance. So it would be better if you know in advance what's happening to an equipment before something catastrophic happens. And that's what we are going to do for today's session. Now, um, the problem with anomaly detection is because anomalous events are really rare, so they don't occur a lot of the time, and you also cannot deliberately make a machine faulty just in order to know what an anomaly looks like. And for that reason, we don't have lots of data for the anomaly events. That's why it's called an anomaly, anyways. But we have lots of data for how the machine works in normal conditions. So we have this problem where we have just very little information about anomalies and lots of information about normal working. And it would be better if we can somehow make use of the normal data in order to come up with a system which would work, which would predict anomalies or a bad event that is about to happen. So obviously, just like I described, we don't have lots of data in the anomaly class. We cannot make use of supervised learning where we can train a classifier. That's not going to work here for the simple reason that we have little examples in the anomalous class. So the way we'll be then doing it is we'll be making use of an architecture called an autoencoder. So what an autoencoder is, it's just a simple, fully connected neural network. You can also make use of something like convolutional neural networks as well, but we would be looking into a simple, fully connected layer. And the way an autoencoder is constructed is, let me share my screen. So a simple autoencoder appears somewhat like this. So we have an initial layer which could be, you can, like, let's call it the input layer, and this could literally represent your data. So let's say our data contains features starting from x1 to xn. You can just simply say that these are our features x1, x2, and xn. And then we gradually so suppose the n here is, let's say, 100. We have 100 features. We gradually reduce these intermediate layers, the amount of units they have. So we can have a second layer here, which would, let's say, have 50 hidden units. And then we can have a third layer, which might have, let's say, dot, 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 25, or let's say 20 um, units. And then, so as you can see, we are gradually shrinking the size of our input. And then we can do, we can go back from this um, reduced set of size to again gradually reconstruct our input. So we can then have another hidden layer with the same 50 neurons, and then another layer, which, let's call it the output layer, where the number of neurons would be the same as the input neurons, 100. Let's call it yn. This is y1, y2, and yn. So we first gradually reduce the input dimension, and then we gradually construct back or output. This part of the network is called an encoder. This part of it is called an decoder, and this is called the bottleneck, NECK. And this entire architecture is called an autoencoder. Now, just by looking at this architecture, can anyone tell me what could this thing be useful for?
So I'm not sure if you mentioned or if I'm giving something away, but the main idea of the autoencoder is that the input and that when you train it, the input and the output are the same, right?
Exactly. So the way you train this, I should have talked about this. The way you train this autoencoder is um, the input to it, which is x1, x2, and xn, and the output are the same. So, of course, we are not going to exactly get back our output to be exactly the same as our input, but the goal is to train it in such a way where it learns how to reduce the set of dimensions as the model progresses. And then, once you have these reduced set of features, use them to construct back the original input.
Yeah.
So, the way you train it is you provide the input and output to the model to be the same. So, previously, remember when we wanted to train a neural network, we would pass X train and Y train to the model.fit function. In this case, the way we'll train it is that we'll pass to this model.fit this X train twice, X train and X train. So we want this model to squeeze the input data into a reduced set of features, and this is called the bottleneck. It is also sometimes called the latent space. So latent space just simply means some reduced number of freedom, dimensional freedom that you have, which you task this neural network to represent your input data. So even your original dimension was 100, but you want this to represent the same data with just 20 dimensions. And then making use of those 20 dimensions, you want to reconstruct back your original input. So one possible application which makes sense is we can make use of it for compression, where we have lots of input dimension. We can compress our data where we just only need now 20 dimensions to represent it, and then we use the decoder part to reconstruct back our original input. So now we just have to store the weights for this decoder and the weights for the encoder, and we can compress our data based on this architecture, right?
Yep.
That's one use of it. But there are lots of other applications for this autoencoder. And one application that we are looking is anomaly detection. But another cool application of it would be noise removal from the data.
Mhm.
So let's leave the noise removal for now, and let's talk about how can we make use of this architecture to do, let's say, anomaly detection. So the example problem that we are looking into is that we have some industrial machines where when they operate, they generate these sound waves. So you can also take their vibrational data where you place a accelerometer on top of it, which measure the vibration. But we are not looking into the vibrations. We are looking into its sound signal. So we place a sound sensor near the machine, and when it's working, it is recording the sound of it. And we have lots of data for the normal condition of the machine, normal working of the machine. So we have what we'll do is we'll take our data, um, the sound signals, and we will train this autoencoder uh, for these sound waves. So what we'll do is it will take the sound waves and it will compress it to this latent space and then reconstruct back the original signals from it. But since we would have trained this model for these normal sounds, Of course, this output that we are getting would not be exactly the same as this input, because when you reduce the number of dimensions, some of the information is going to be lost. The goal is not to lose too much information. But when we get back our output and we compute the difference between this original input and this reconstructed input, there would be some error. But because we would have trained this for these normal sounds, that error would be, let's say that would be some amount. Let's call it error 1. Now, if I take a signal which does not appear in my training set, which is some outside signal, an anomaly, so let's call it S1. If I feed that signal and this model reduces it to this latent space and then reconstruct back that signal from it, that original input from it, the error that it is going to generate for that signal is going to be larger than the error that it was generating for the normal, um, for the type of data that I trained this model on. Does this make sense? Is it plausible?
Yep.
So it's generating smaller error for the signals which we have trained it on. But of course, if you throw at it something which does not appear in its training data, that error is going to be slightly bigger than what the what it was on the normal signals. And then we can just simply put a threshold on the error. So if now I want to, let's say, detect an anomaly, I can record the sound of that machine and I can pass it from this autoencoder. It will generate. It will first squeeze it this to this latent space, then reconstruct back the original signal from it, and then I'll compute the difference between what I fed at the input and what I got at the output. And if that error was larger that error one, I would say that this is something which did not appear in its normal working. So obviously, if it's not appearing as normal working, this is something that is an anomaly, or you can deduce from it that something is wrong with this machine, just based on the way the way it sounds. And this is literally the whole idea of doing anomaly detection using this autoencoder. If you have any questions,
Interesting.
I would love to answer.
No, it actually makes sense. Just to confirm, the data we're normally training it on is like, I'm talking about the normal audio, right? So we have the most amount of normal audio and the least amount of, let's say, any error. The reason we're getting a less error for the normal sound is because we have more data to back it, right?
Yeah, because the
Is
model has seen that thing during its
right.
training.
Yeah, that's what
So
I'm saying.
yeah, so if you compare, like previously when we were training a neural network, typically what would happen is that the loss on the training was slightly lesser than the loss on the validation data, where validation data is the data that it has not seen before. So we're making use of that small difference of error in order
Mm-hmm.
to detect something which does not appear in the distribution which we used it to train. So
Right.
because that would be slightly outside the distribution, it has not seen that sample, and that's why we would deduce that it is something which is anomaly.
Yeah, that makes
Now,
sense.
yeah, so one way of doing it would be to feed the raw sound samples directly to this model, but that's not what James has done. What he has done is he has taken the features of the normal. Um, he's done handcrafted feature extraction. So he's using MEL's, what is called MEL spectrograms. This word MEL just simply is because we are using a logarithmic scale, but forget about the MEL part. What a spectrogram is so do you know about Fourier transform? Suppose this is a sound signal. Do you see this color?
Yep.
Okay. I was working with a client and he told me he can't see this. Um, so if you have the sound signal and if you do Fourier transform on it, the output is the frequencies in this sound. So you
Right.
have these lower end frequencies and higher end frequencies. This is normal Fourier transform. The problem with Fourier transform is you completely lose the timing information in the signal. Now all you have is the frequencies, but you don't have any information of the time, like when is this frequency occurring, when is that frequency occurring, when is that timing is lost. That's the drawback of Fourier. And if you work with the pure time domain, then you don't have any information about the frequencies that are appearing in this sound. So spectrogram kind of works in the middle. So what it does is it chunks the signal into these, divides the signal into these chunks,
Oh,
and then it computes the Fourier transform of these smaller regions. So now this region will have its own frequency distribution. This region will have its own frequencies, and this region will have its own frequencies. And then you can combine this information into a 2D data.
yeah,
So let's say you'd have on the x-axis, you would, let's say, have the frequencies, and on the y-axis you would have time. Or you can also describe it the other way around. So um, maybe it would be better if I do this the other way. If this is frequencies and if this is time, so that chunk comes here. It has this frequencies. The second chunk comes here. It has this frequencies, and so on. So you have this 2D data, and this is what a spectrogram is. And then you can make use of the spectrograms as features to this autoencoder, which then squeezes those to the latent space and reconstruct back the original output. Now you'd be asking, why are we using spectrograms? Well, it turns out that pure using pure raw samples with the model doesn't usually perform better. And that's why we have to sometimes do this handcrafted feature extraction. For sound signals, usually the feature extraction that we use is typically a Fourier analysis where we compute these frequencies from it. But you can literally do this whole exercise without using spectrograms. You can try it with the raw sound samples, and it would be interesting to see how it performs without those feature extractions. But this is just one extra detail that I wanted to talk about. And now, all over to you, James.
yeah, that is quite interesting. So in the example that we're using, we have these raw audio files from the machinery, and then we put it through the spectrogram. So um, if you, Burhan, I'm not sure if you know much about sound, but basically, like a normal sound file is just pressure over time, so it's like the actual sound wave. Um, so if you would have like, just like one long beep in a sound file, that'll show up as a sine wave. Um, in a Fourier transform, that would show up as just one peak because it's just showing the frequency. I don't know if
Right.
that makes sense. Yeah. So it's interesting to think, and we haven't really looked into it too much, what would happen if we would train this neural network on the time data. What we did was we used the spectrogram. But that's something that we're curious about. So, okay, here's the code, and this is based off of a project from Naveed, which is on his GitHub. But I sort of combined the different files into one notebook, just so it would be easier for us to walk through it. The main thing that's going to be new for you is going to be the autoencoder, but that's really just another neural network that is what uses the same type of layers that we used before. It just starts with a larger layer and then goes to a smaller and then goes back to a larger layer, whereas previously we were probably doing it the other way around.
Right.
So that's the main difference. And the other difference will be, how we process the audio, and then maybe how we look for outliers. So this data here, if I would just go to this URL, is a huge and really huge data set of audio files. If you look at the whole data set here, I believe it's a total of maybe 100 gigabytes. Yeah, for everything. But we don't choose all of the data. We can choose a certain type of machine.
Right.
So we can choose like a fan, a pump,
Slider.
Yeah, slider. So, and then I think they've adjusted it by decibel levels. So for this, um, I've just selected the valve.
Right.
That looks kind of interesting actually when we plot it.
Hey, what
So
does
that
it sound like though?
All
What
right,
does
James, can you tell
play
us
the
why
sound?
didn't you use fans?
sorry.
Can you tell us why didn't you use fan?
Okay,
Fan
so
is the machine.
what a valve? I think what a valve sounds like is like click, 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 click.
Uh,
I think that's what a valve sounds like. I think, but actually I have to listen to it. The fan, now fan sounds obviously like. Now, now I have an example. I have. I'll find. Do you want me to show the example that I sent you, Naveed?
Yeah.
When I looked at the fan data for the first time, I was like, oh, because
you were blown away.
well, I was blown away by how obvious it was. Now, maybe there's a lot of like intricate details that we don't know about. But when I looked at the fan data, I was like, well, Naveed, is it possible that maybe a broken fan is just louder? so, so I don't
That's
know.
actually fair. Yeah.
So maybe that's why it's good to do some data exploration as well.
Yeah.
Um, because yeah, if the broken fan is just louder, then we could just average
Yeah.
the volume and use maybe a linear regression or um, a logistic regression, for example.
Mm-hmm.
Yeah.
But that's just one audio file that I looked at.
Mm-hmm.
Um, so we'd really have to look a bit further. Now that's why I moved to the valve. I thought the valve could be more interesting,
Right.
and we'll see what that looks like in a minute. Um, so I just used one of these data sets here because it's already a ton of data. You can see it's already like
True.
3 GB. So I just wanted to make an example. The rest of this code is just splitting up the files into training and testing paths.
Mm-hmm.
There's some helper files here, which you really, for this case, I mean, for your project, you might not be doing audio. So in that case, like half of this code, you could just delete it.
Right.
Most of the code here is for dealing with audio files. So
Mm-hmm.
this takes an audio wave file and then converts it into a NumPy array. Pretty simple because it's just each item in the array is the amount of pressure at that point in time. Um, Now this plots the valve, right? So in this case, the valve that's broken is clicking quieter and faster, but we don't know if that's true for all of the data. This is just one example, and what this function is exactly what Naveed was saying before. This is a spectrogram, and
Right.
so we're converting from the time domain to the frequency and time domain. Um, we input the sampling rate, the number of I guess time buckets or frequency buckets, and that sort of information, and that gives us out a new set of features with frequency data. Now, yeah, of course, really understanding the data here is key because we don't know what's more important. Is it maybe volume is more important? Maybe the volume is more important. In that case, this would be a poor, um, like, yeah, a poor choice of features.
Yep.
Um, so this does the same. This does the exact same thing, but it just loops over all of the files and then generates those features for every file. Um, and here we do that. We generate the training data. And this takes a few minutes to run. Um, and this is the autoencoder. So it should look really familiar to you. It does, right? You guys remember this? Cool. So yeah, exactly as Naveed was saying, it's just a regular network with dense layers, 128, 64, 32, and back up. Um,
I'm
let's
curious, how did you come up with these layers? Like,
It
yeah,
is just, yeah, I mean, the same way we come up with those of any neural network. So just experiment with it.
right?
yeah, yeah. There's no magic to it.
Hmm.
I mean,
But
it's all magic, rather.
yeah, but you have to make sure that you gradually squeeze the input to reduce dimensions and then reconstruct back the original one. So if you see in the last layer, James has used non non-linearity of none, meaning there's no activation function applied. And we would like to do it because we would want our original input, so that could also contain some negative values, some positive values, and that's why
Oh,
we have left it at none. And the number of neurons that we have is the same as the input shape.
Yeah,
So at the input we have the input shape, and then at the output we also have the input shape.
interesting.
yeah. Hmm. Hmm. Interesting. So, this here is just training the model, and then this is the, as you can see, the input and the output data is the same.
A epochs equals epochs. Did we define it?
Yeah, that's just there's some settings that have been defined up here.
Okay.
Number of epochs and the batch size. And this takes a this takes some time to train.
Hmm.
We can see that the loss goes down really quickly at first, and then it sort of evens out. So this is what this looks like.
Victor has asked a question.
Oh,
Why
Where
why
does it
doesn't the
know?
model have an activation function?
okay.
So we
That's
do
here.
have activation functions in the hidden layers, but at the output, just like I described, uh, we want the input, original input, um, that this model should be predicting.
Yeah,
And because the input, just like James said, sound samples are just a pressure in time, could also contain negative values. Um, we don't want to modify that. So
yeah,
that's why the activation is none. If you would have used a ReLU, or let's say a softmix or anything that would have altered the data, we don't want that. We want our original input, and that's why activation is none, which means no activation function.
right. The activation function normally will, yeah, convert something into a value between 1 and 0. We want to preserve the original type of information that we had. This, if we look at this, it's extremely symmetrical, isn't it, Naveed? The whole thing.
Yeah, and it is required to be symmetrical. Um, so whenever you see an autoencoder, the input, the encoder part is this exact replica of the
Right.
decoder part, only flipped.
Yeah.
So it has to be this way. And an interesting variation in an autoencoder, which is called the variational autoencoder, is for the latent space, they don't choose a fixed set of neurons, just like we have used here, the 32. What they do is they map it into a distribution. So they compute what is called the mean and the standard deviation of the distribution rather than the exact um, latent space neurons. And the use of variational autoencoder is that because you are now transforming the data into a distribution, you can sample from that distribution. And sampling from that distribution means you can create something new, which looks similar to your input. So variational autoencoders is a generative model which can be used for generating new samples of a data. So you can create new pictures if your input data is pictures. You can create new sound signals if your input data was sounds, because you are now squeezing that information into a distribution. You are learning a distribution and not a fixed set of inputs. fixed set of values. So variational autoencoders are once they have been once they were used for generating stuff, but they are not very successful as compared to the other things like the diffusion models and the transformers.
So actually, I have a question now. So the the autoencoder consists of this encoder, and then we have one layer at the middle, and then we have like a decoder. Um, is it is it significant or is it important that the encoder and the decoder have separate weights? Or in other words, like, is the decoder, if you would take the whole thing and then flip it backwards after it's trained, does that make a big difference? Do you know what I'm saying?
Hmm. That's an interesting question. So you're saying that if we take the same weights but replicate them, won't it be able to reconstruct the input without using separate weights for the decoder? That's what you're saying?
Yeah, yeah, that's sort of what I'm asking. Like, is it important that could you take the encoder and then just reverse it and create a decoder, or is it important that they have their own separate sets of weights?
Let's think about it. So what the encoder would be doing is that it would be taking input from the last layer and squeezing it further to a reduced set of weights.
Mm-hmm.
So it's kind of a one way because those weights would be used to take this input and squeeze it.
Yeah,
But you cannot make use of those weights then to go back to take those inputs and go back to the previous layer. You see the problem here?
but then you would have
Yeah. So so you would, I mean, it's a one way. You cannot make use
one
of the
way
same weights to.
because of the nonlinearities.
Yeah, and because of the nonlinearities as well, they also play a part in here. But the way I'm looking at it is, those weights could only be used to make the data squeeze further and not the other way around.
Right.
Uh, but this is something that, I mean, it's an interesting question.
That makes sense.
We can have a look at it.
Okay. So now we've trained the autoencoder, right? Um, we got down to the MSE loss here of,
Mhm.
I guess, 5. So now the step here, there's a lot of loops in this code, and what this final step is doing is it's taking each item in the test data set, it's running that through the autoencoder, then comparing it with itself, with the original data that we ran through the autoencoder, to see how much does it differ after it's been squeezed down and then decompressed out of the autoencoder. What is the how close is it to the original value?
Right.
And then we make a so we do that for all of those audio files, and then we chart that on a histogram. So I have to scroll. Here it is. It's at the bottom here. so then let's see. Can you see that? Let me make that a little bit easier. So then we chart that on histogram. So here on the x-axis,
Hmm.
so think of this as a bunch of little blocks of this size,
Right.
and each block is one sample, one sample that was processed.
Mm.
And what we're seeing here is that in general, the anomalous signals have a higher error after being auto-encoded. I don't know if that's a word, but after being auto-encoded, um, they'll have higher error, whereas the normal ones will have lower. And so we can just see that the amounts, for example, the number of anomalous signals that had a um, an error that resulted in an error of 6.5 was 14, and no normal signals had an MSE of 6.5. Interestingly, there are some normal signals that also had some high error, but in general, we could come up with a threshold that would, I don't know, maybe get 80-90% of them. Yeah, maybe 8. Yeah. So that's what the final step is actually setting a threshold here, and this threshold here is actually taking um, the it's actually so we take the mean of the MSE for the normal one for the blue ones for the ones we know are normal, and then if the MSE goes 10% higher, then we call it anomalous. That's just the heuristic that we chose for this. And then we have a completed model that we can use to detect anomalies. So the the error threshold here was set to 6.45. So if we look at our chart here, that's going to be right here, right? So that means anything above this error is going to be anomalous. All of these red ones here then would become false negatives, and these
Right.
blue ones here would become false positives. So let's see how that comes out. That gives a accuracy of 67%. What do you guys think?
And that
Amazing.
was fun.
What?
I said that was fun.
Cool.
We got we got 67, right? But we can still tweak around with the layers to see
Yeah.
Yeah,
how
Yeah.
different it gets.
your job is to get a score of, let's say, 80.
80? That's a
That's
huge leap.
it's possible. You can also experiment with just using the sound samples, raw sound samples, without bothering about the spectrograms.
Right.
Because James and I had a discussion about it, and he said it would be more useful if we do it without the spectrograms, because it would be then making use of the amplitudes rather than the frequencies. And that way, because we're just simply putting a normal threshold, and the error is just simply the differences between their amplitudes, it would be better if we work with the amplitudes. But that would be interesting to see if it performs better. I think I didn't check it without the spectrograms, but you guys can.
So I have the question of, but if we would do it without the spectrogram, then we would still need to downsample somehow this data, right? Because it's too much data to pass into the neural network as it is.
Downsample, we can also do the segmentation, where we take certain windows of this
Right.
input
Okay,
signals,
that
and
makes
not
more
use the
sense.
entire sen. And James, the question that you asked, interestingly, I didn't know about this. Let me share my screen.
Okay.
But there is an autoencoder which does that.
Yeah. No, I just want to say that makes more sense to use the moving window, because then also you have translational variability as well that you can handle with that, right?
Okay, do you see my screen?
Now we do. You've got it. Okay.
Okay,
Well, now we
so
do.
ask you the question that why do we need separate weights for the decoder, and why cannot we make use of the encoder weights? And it says in theory you could use the same weights for both the encoder and the decoder and autoencoder by transposing the weights of the encoder to reconstruct the input. So what I was what I said previously was, how can you make use of those weights to squeeze the weights that squeezes it to the reduced space? How can then you make use of them to reconstruct back? But it says you can transpose the weights to reconstruct the previous layer. And it
Yeah.
says this idea is known as a tied weight autoencoder. I'm not sure if this ChatGPT is right now hallucinating something. You guys can also
No.
verify this. But there's a term called tied weight autoencoder, where the weights in the decoder are constrained to be the transpose of the weights in the encoder. But then it says, however, in practice, using separate weights for the encoder and the decoder has several advantages. One
Yeah.
of it is the flexibility. Having separate weights allows the encoder and decoder to learn different mappings, providing more flexibility in the learned representation. Because if you then constrain it to use the same weights, those weights would not be able to then learn complex features. Like it would, they would then just work for simpler data. But when the data becomes complex, like sound waves, images, um, it would struggle with that. And then it says the activation functions applied after the weights in the encoder and decoder can differ. Using tied weights restricts the model to symmetric nonlinearities, which might not be optimal for learning complex
Right.
representations. Do you understand what this is saying? Because I don't.
Intuitively, I kind of get the idea that if you if you have a model that's completely symmetric in weights, that the second half, I mean, obviously the second half of the autoencoder is just undoing what the first half did,
Hmm.
exactly undoing it.
Yeah.
Therefore, for your training data, your error should be very low.
Hmm.
Well, possibly.
And then it says empirically autoencoders with separate weights often perform better in terms of reconstruction. And finally, in some architectures, the encoder and decoder might have different structures, yeah, making it impractical to tie the weights. So if you construct the encoder in such a way where it's not symmetrical, then of course you cannot make use of the same weights. But that's not a huge issue. We can make it symmetrical. Performance, maybe performance was one principal reason that they use different weights. Uh, the first and the third point can both mean the same thing, but the second one I'm still trying to comprehend what it is saying. But just to have a comment on what James said, yes, there is something called tied weight autoencoder where you can constrain the model to use the same weights as the encoder.
Yeah, and I also was curious if it was a hallucination, and I actually checked, and it's apparently people have actually built these before. So
Uh-huh.
this is one
That's great.
case, and you can see that they're defining three layers, and then they're defining the next three as the transpose of the first three.
Amazing.
So it's
Right.
real, but it's not. It doesn't seem to be very common.
Yeah, Burhan and Victor, it would be better if you teach me and James something and construct this autoencoder and train it on this data and then come up with your results. We can learn a few things from you as well.
Yeah, or
I
invent
mean
something.
that would be the project. Would
Yeah,
that be the project, or are we supposed to do
if
something else?
if you people are up to it, that could be a good project. It's literally it can be. I mean, s- anything that is slightly different in machine learning, you can write a research paper on it these days because the field is in its infancy. So that could be an interesting research problem to look at. I didn't hear about this thing, this tied weight autoencoder before.
Maybe there's a reason why.
The reason could be it didn't work that well, and
Some guy like me, 10 years ago was like, oh, I wonder if what this would do.
yeah.
So, um, just want to go back to this feature extraction aspect. So, for me, I think the first most interesting thing about this model is that frequency bit, and your idea of using maybe like shifting, how'd you call it, a window.
Yeah, windowing operation, like segmenting the samples
Yeah,
into windows.
that seemed quite interesting, as well, because what I do notice just from visually looking at a lot of this data, this one in the fan, is that the amplitude of the wave overall seems to be pretty important.
Yeah,
Because, for
for the normal
example,
signals it is high, and then for the anomalous ones it is lower.
when we look at the Mel spectrogram, it's basically comparing. the amplitude of, or the magnitude of this frequency versus the magnitude of other frequencies, and that could be very similar for these two. But the the overall amplitude is very different. So I wonder what else. There's so many ways to work with audio. Yeah.
Yep. People even construct spectrograms and then they make images of it, because spectrograms is 2D data then, and you can plot such a thing.
Ooh.
And then they take the spectrograms and construct a CNN and make use of CNN to do these things. So just like you described, there are multiple ways to play with sound data.
So if we would train a CNN on this two-dimensional data, we could do sort of a binary classification, but
Yep.
we don't have a lot of anomalous data.
But you can construct an autoencoder, a
A
CNN
CNN.
autoencoder.
You could make a CNN autoencoder. Now, I think there's a project.
Mm-hmm.
But
Yeah,
there's a lot
that
of
would
work.
be fun.
So first,
Yeah.
first I mean, there's not a lot of work. You only have to tweak the model because spectrograms are already computed.
Yeah.
So you just need to make images of it,
Right.
or don't even make images of it. Spectrograms data is already, I mean, it's a 2D data, or was it a 2D or 1D? Can you,
It's
James,
2D.
go to the,
Yeah, it's 2D. On one axis, you have the time, and then on the other one, you have the
yeah, but in
frequency.
the function, did we flatten it?
Oh, did we flatten it? So it returns a 2D array. For each row
Okay.
is your vector, so it's 1D.
Yeah,
Well,
it's 1D. Can you go to the Lebrusa feature mel spectrogram? So this Y, and then scroll a little bit more. Power to dB, so that's computing the mel part, and then I think in the last line.
sliding windows. It is
Oh.
using a sliding window. So maybe it's 2D actually, because it's doing the sliding window, and then for each window, it's doing a spectrogram.
Mm-hmm. Log mel spectrogram,
Yeah.
and then it's returning the features. Can you scroll down to this generate data set?
Yeah, that's just looping for here for every file.
Okay. And scroll down to the model. What I'm confused about is why haven't we specified this as a 2D data to the input shape? In the input shape, we have one dimension. So if
Right.
it was 2D, we should have specified it here. The dimension is a
So here we
2D.
go. Yeah, so the input shape is flattened,
Mel's
obviously,
preference, yeah.
is the flattened shape. And then here we're getting the features and the dimensions, of course. Okay, then we have 10. Set equals. Oh, I think I see.
Mm-hmm.
So this is not adding this is not creating an array of arrays. It looks like it's appending each new array to the end of an existing array. See what I mean?
Yeah. Yep.
It's just sticking them all together
Hmm.
in a beautiful Pythonic script.
Yeah, so spectrograms are usually a 2D data, but then they are appending it as a 1D. So what Burhan and Victor can do is modify this code such that it returns it in a 2D array, not a 1D, and then construct a CNN autoencoder to train it in on the 2D data,
Right.
and the rest of the stuff stays the same. So if you manage to do it, James would give you $1 million each, and
I'll,
if
I'll
you
be
didn't if you
looking
didn't
around.
manage to do it, then you will pay me $1 million.
Be looking around for some sponsors. Okay. Yeah,
But
no,
yeah,
I think this is really the $1 million prize, guys. If you can do this, and maybe I mean I guess you guys could work together. No reason why not.
Yeah, that would be fun.
Um,
Let's see.
yeah, this is definitely like a new level of challenge. So I think it would be interesting. Cool.
yeah, and I think James, that was the last session with this class.
Yeah. So yeah, we can do. Of course, this is the official end of. After this, well, we'll have another session, of course, to go over the projects,
Projects.
the final projects, and the results of those, of course. But as far as like um, the duration, that's how long we wanted to make the course. Um, but yeah, maybe we'll do. I think we need to have like a bit of a break just to go over all the feedback and process everything that happened and think of ways that we want to improve the course. But yeah, we'll
Right.
let you know after that what's next.
And
Sweet.
Brian and Victor, did you learn anything from this entire exercise?
Yeah, of course we did. Like the whole course, right?
Yeah.
Yeah. Like we started off from the basics, and then we stepped up like with each gradual step, and yeah, I personally learned a lot of new cool stuff that I can later explore as well. So yeah, you guys
Mhm.
have my gratitude. Thank you.
Thanks for working hard. Victor says, "Yes, I did. I learned a lot,
Amazing. So
but it's
this
not over
was
yet. You still have to finish this last project. Okay,
Yeah, you can't run away from the
be
project.
very critically reviewed.
yeah.
Think of this as your PhD thesis. Okay, like that.
Yeah, I mean, there's so much potential for the simple reason that this field is new, and you can literally get a PhD by taking ideas from machine learning and finding a useful case scenario in some different fields. So if you can merge it with whatever domain you are looking into, you can do a PhD easily, a master's even more easily. For my own master's, what I did was I simply took the traditional algorithms, the SVMs, the XGBoost, and a simple fully connected neural network, and I trained it on. So the equipment that I was looking into was an electrical transformer, and the data that I had was magnetic field patterns, which I um, detected outside the the steel tank of the transformer. So if something wrong would happen, it would generate one kind of patterns, and if during the normal operation it would generate different patterns. So it
Right.
just was a simple binary classification problem. Um, but because so like if you look at it, it's a very simple thing, but still it's a novel technique to do fault detection, because previously the way fault was detected was manual introspection. So something wrong would happen and then people would report it, and then the utility would come and fix it. But now if you can have a learning algorithm, it would automatically notify that something wrong happened. So as you can see, the point that I'm trying to draw here is that there's a huge potential in machine learning field. You can There are like thousands of ideas that you can work on. Even if you don't do want to do your masters or PhDs, you can just simply do a practical project, identify a problem in your surrounding, and just simply gather some data and construct something useful. And who knows, your model could be in the news articles the next day. So I saw something. There was a girl, a small girl in India somewhere, and she was, I think, working with. So she detected. She constructed an app which was doing the air quality monitoring. So the toxicity in air using I think she used images, and I'm not even sure how images would detect pollution in the air. Maybe it does, but that thing was then featured on the TensorFlow website, and also they talked about it in live demos. So there's huge potential, and it is something that you can literally work by sitting on your laptop. You don't need to do lots of there's little physical work involved. Everything is available out there. If you don't have GPUs, Colab is there to help you. Um, if you are struggling with the code, ChatGPT is there to help you. So huge potential. You guys can really make something useful.
Interesting. Because I have like ideas that I want to use in my Head Starters Fellowship program. Because in the final project, I would personally be using something related to machine learning. So I'll keep you guys in touch.
Cool.
Looking forward to it.
Thank you.
Okay,
Okay. Shall we
I
meet?
will. Uh-huh.
Um, let's stay in touch. How far along you guys are on the project? If you want to take, what do you think, Naveed? Maybe they can have a little more time to actually do this rather than just the weekend. You know what I mean?
You are
That would
asking
be
when can we
nice.
meet again?
Yeah, because if we just give them the weekend, then it might not be enough time to finish this project, right? So maybe they need a whole week, for example.
Yeah, so it's literally up to them. If they can, whenever they did the project, you just need to notify us, and
Yeah,
we can come.
perfect.
Fair enough.
Great. Well, best of luck.
Thank
May
you.
the odds be in your favor.
Needed that.
The AI. Right. Great
Thank you.
work, guys. Thanks, Naveed. Thanks, Burhan.
Welcome. Goodbye.
Bye.